are present here. Myself, I am Dr.A.Ram Kumar, Associate Professor, Head of the Department of Electrical and Electronics Engineering, Kalaslingam Academy of Research and Education. And now I am going to take the fundamentals of wind energy conversion system. Why we are going to choose this topic? Because nowadays we are facing lot of power issues. Because due to the shortage of coal, some issues in the nuclear power plant, we are moving towards the renewable energy sources. In renewable energy sources, lot of resources are there: solar, wind, biomass, geothermal, ocean technology. Lot of renewable sources are there, but everything is having certain advantages and disadvantages. Worldwide, we are much more focusing about the two major renewable sources for generating the electrical energy. The first one is the wind energy conversion system, wind energy. The second one is the solar PV systems. So the lot of research work is going on here. We are using the standalone wind energy system or grid connected wind energy system or hybrid wind and solar integrating systems. Nowadays, the lot of research work is going towards that direction because we never imagined the world without the electricity. So the electricity is one of the mandatory component to run the world every day, every minute, every second. Electricity is a mandatory component. Whether small scale industries or large scale industries or domestic side or industry side or MNC, whatever the companies, everything is running only based on the electrical energy. If there is an absence of electrical energy, automatically all the works comes to zero. We cannot do anything. So uh, we must provide the good quality of electrical energy to the customer. So I proudly say we are a electrical engineer. Nowadays, the computer science department or IT departments are doing very level. But anyway, the core related departments, that's electrical, mechanical, civil. Uh, Nowadays, we are somewhat lagging related to the placement activities only. But electrical is the mandatory component. It's an essential component to run the normal life also. Is it correct, student? Is it correct? Anybody give the reply? Is it audible,
Yes, sir.
students? Yeah, okay. So, in future, we are moving towards that direction only. That's a renewable energy sources. So, within 10 years, every home also, we are using the separate solar PV system for generating the electrical energy. Nowadays, the industries, HT industries, textile industries, other industries are generating the electrical energy through the solar systems. So very soon, that solar energy will be utilizing in the home for generating the electricity. Okay, sorry, student. So why we are going to choose the wind power? What is the necessity? Why we don't take the tidal power? Why we don't take the biomass? Why do we don't take the ozone technology? Means in renewable energy sources, we are having the we are concentrating the two powers. One is the solar and another one is the wind. But the solar, we can get the maximum efficiency at 25% only. At very uh, huge availability of solar, we can get 25%. But wind, we can get almost 50 to 60% is also possible. So then only in our India, we are much more concentrating about the wind power generations. Here, that separate ministry is also there. Separate ministry is also there. That's the Ministry of New and Renewable Energy. That is simply called as the MNR. So the lot of research work is going under the Ministry of New and Renewable Energy Sources, and they are framing the policy for the renewable energy sources. In particular, they are very much concentrating about the solar, wind, or hybrid of solar and wind with the grid connected system, with the interconnected of grid. So here in this MNRE as incorporated with the Center for Wind Energy Technology. So Center for Wind Energy Technology, that is a CWET technology. So I think most of the students hear this word CWET. Actually, they are focusing very much focusing about the wind energy. So it's a Center for Wind Energy Technology. They are much more focused about the wind only focus about wind based on the because the India is the very populated area and the area occupation, the cross section area of the India is also very huge. So the CBET taking a lot of historical data based on this estimation, the Gujarat, Karnataka, Andhra Pradesh, Tamil Nadu, and Maharashtra, lot of wind potentials are available because for example, you just take this is the shape of the wind, shape of the Indian country. Okay, so these portions you just take up to these portions there is an seashore area only. So in the seashore area, lot of wind potentials are available. Lot of wind potentials are available. So if you utilize that energy, so we can meet out the demand which is required by the consumer. Okay, so then only we are moving towards that directions. Solar, it is also having the huge potential, but apart from that, solar is having one of the major drawback. Um, During the April, May, June, July period, we can get the good quality of energy from the solar. But during this period, December, November, December, January, so the availability of solar energy is very minimum only. But anyway, we are moving that directions also. But if you see this seashore area, 24 cross 7, that is the 365 days the wind is available. So 365 days throughout the year, we can get the sufficient amount of wind energy. So you just take the reason Gujarat, Karnataka, Andhra Pradesh, Tamil Nadu, then Maharashtra is also there, and Andhra and Odisha, West Bengal. So the lot of wind sources are there. Okay, lot of wind sources are there. So in the seashore areas, almost 365 days we are having the wind potential. Then only the government is very much concentrating about the wind energy. So they are established this wind energy sea. Okay, so in the seaward, what's the major role? It's a vital contribution of the wind energy industries. So how do you generate the electrical energy by the wind power plant? How to utilize that electrical energy by the consumer in the proper way? How to integrate that with the grid system in the optimal manner? So everything is carried out. Everything is carried out by the Steve. So here I just take students. The screen is visible to you. Students, the screen is visible. Anyone give the reply to me? Bhuvanesh?
Yes, sir.
Yes, its screen is visible. Wind energy region in India. Can you able to see the screen?
Which one, sir?
Wind energy region in India. India map now open it. Can you get
Yes,
the
sir.
screen?
Slide மட்டும் open ஆகுது.
Oh, slide there. You just wait.
Slide
I think
open ஆகுது.
some network issues.
All windows கொடுத்தீங்கன்னா வரும். Okay, sir. Now it's available.
Yeah, okay, okay, yeah, yeah, yes, yes. I think just a minute.
சார் இப்போ வந்துருச்சு.
Uh, okay, Bonis, can you hear me?
எஸ் சார், கண்டினியூ சார் ப்ளீஸ்.
Yes. Okay. So here, based on the CBET estimation, some historical data are there. Here, this based on the wind power density. Wind power density, that's a power watts versus square meter. We can take some availability of wind resources. The red line, it gives the 200 to 250 watts per square meter square, and yellow line, it gets the 400 to 500 watts per meter square. Okay, and this white area, that's almost availability is very very minimum. So these historical data are uh, estimating the availability of wind power in the India. So this data are taken by the CBET. So here I just go to the next one. That's the installed grid interactive renewable power sources. Actually, this data is taken at the June 2020. So what are the availability of wind power? Okay, what are the availability of the wind power? Okay, so here this wind power, this green line, you just take the green line. Here everything is a renewable sources. Almost it is 45 a percentage we can install grid interactive renewable energy sources. Okay, so the next one we move to the solar energy. So we are concentrating about the solar energies, and the third one we are generating the electrical energy by using the biomass. This is the wind power, solar. This is the biomass. This is the small hydropower plant, and this is the this black lines. You just see this line, waste to power management, power generations. That is very minimum. You can ignore this value also. So this is the installed capacity of the renewable energy sources. So based on this chart, we can get the wind power produces 45 percentage renewable sources than the others. The next comes to solar wind energy, that's a 36 percentage. Biomass is very minimum only, 12.2 percentage. Small hydro plant is the 5.7 percentage. So from this discussion, what is our conclusion means, the wind power generation is giving the more power to the grid than the other renewable energy sources. So the next one we come to the various types of classifications. Everybody see the windmills. Everybody see the windmills. It's having the two different axes because you are the Tirunelveli students. So in Kaitar side and Muppandal side, lot of wind plants are there. So normally it's having the two different classification. One is the horizontal axis, and another one is the vertical axis. So horizontal axis and vertical axis. What is the horizontal and vertical axis here means? The wind blades rotation is the coincide, that is the parallel with the ground. In our Tirunelveli side and Kaitar side, we are using the horizontal axis windmills only. Vertical axis means the blade is rotating, which is based on the perpendicular. perpendicular to the ground, vertical to the ground. Some research work is also going on in the vertical axis also, but in general, we are normally utilizing the horizontal axis machine. Almost 80% we are using the horizontal axis machine. 20% we are using the vertical axis machine. When compared to the horizontal axis type, few vertical machines are available only in the commercial purposes, but not in popular. The horizontal axis is more popular than the vertical axis windmills. So here you just see the some pictorial. That's a photos for the vertical and horizontal axis wind turbines. This is the horizontal axis wind turbines. You just see here. This is the horizontal axis wind turbines. This is the vertical axis wind turbine. Vertical axis wind turbine. So in general, we are seeing this type of horizontal axis in our country. Almost 90% we are using only the horizontal axis in our India. So in horizontal axis, we are using the 2 blades or 3 blades. So here we will come to the upwind and the downwind facing. So in our India, as per the geographical arrangement, there is a two winds are there. One is the upwind and another one is the downwind. What is the upwind means? For example, if you see this is the ground. Suppose the wind direction is flowing from ground to cloud area or sky area means that is called as the upwind. Suppose the direction of wind is sky to ground means that is called as the downwind. But depends upon the climatical conditions. Our India is having the two different wind structures. One is the upwind also and the downwind also. So that horizontal type of windmills are much more suitable to the both the winds. It's suitable to the upwind as well as the downwind also. Okay, in vertical axis, you just see this. Sorry, students. This is the vertical axis. So here, this blade you just to see here. This is the vertical axis blade. Vertical axis blade is there. So in this vertical axis blade, you just take it is perpendicular. It's a perpendicular to the ground potential. Very few places only we are erecting the vertical axis blade. Almost we are more than 90%. We are using only the horizontal blades also. We are using only the horizontal blades. So here you just take some schematic representation of the wind turbine. This is the vertical axis. This is the vertical axis. This is the horizontal axis. Okay. So sorry, sorry. This is the horizontal axis, and this is the vertical axis is there. Okay. So you come to this horizontal axis. This is the blade. Okay. We see the 3 blades. In general, we are using the 3 blade structure in Tirunelveli side. Okay. So this is the rotor diameter from this portion to this portion, that is specified as the rotor diameter, and this is the rotor blade. Actually the shape of the blade is it's look like this way. For getting the maximum efficiency from the wind, we are designing some special structure of the wind blades, and this wind blade is mechanically coupled with the generator. Okay, this is the wind blade is there. It's a mechanically coupled with the generator through the gearbox. Through the gearbox, okay. And this is the tower. This is the tower area, and it is erected with the ground portions. Erected with the ground portions. Actually, one wind plant, for example, 2 megawatts wind plant, it takes minimum 2 to 3 crores. 2 to 3 crores it takes the cost for single wind erections. In vertical axis, you come to here. In vertical axis, here this is the rotor blades. So from this edge to this edge, rotor diameter is there. The from top to bottom portions, this height is called as the rotor height. Okay, so you just see that wind blade is vertical from the ground potential, vertical from the ground. Okay, so it is mechanically coupled with the generator. This area is the gearbox. Okay, so this is the structure of the wind turbine, horizontal axis wind turbine as well as the vertical axis wind turbine. In vertical axis, okay, some blade designs are there. Some depends upon the availability of the wind potential. It's having some structures. You just to see here, it's almost semicircular shape. Okay, then some structures of the blades is there. So here, this blade, each and every blade, the phase displacement is 120 degree here because we are using the three blade system, 120 degree displacement. So depends upon the availability of wind, we can use the first category or we can use the second category, and the third category is also there. That wind blade is having the curvature one. It's having the curvature structure, but anyway, the angle displacement of these wind blades are 120 degree because everything is equally distributed, equally arranged. Okay. So now we come to the horizontal axis. I already told this discussion almost more than 90 percentage. More than 90 percentage we are using the horizontal axis wind blade in our India. But in research aspect, we are utilizing the vertical axis wind blade, and some, for example, Gujarat area, we are using the vertical axis blade also. But the percentage of utilization of the vertical axis blade is very minimum when compared to the horizontal axis wind plants. Here, this is the tower portions. Okay, this is the tower. Here, this wind blade is there. This wind blade is connected with the generator. This is the wind blade. Is connected with the generator through the gearbox. Because why we are using the gearbox? Why we don't directly connect the wind blade with the generator means the wind speed is not a constant one. With respect to time, the wind speed is varied and direction of wind is also changing. So that, but in generator, we must give almost constant speed, not exactly constant speed. Then only we are using the variable speed generator here itself. So by using this gearbox, we can give the almost constant speed to the generator. We are nowadays we are using the very sophisticated gearbox for giving the constant speed to the generator. Okay, so this unit is called as the hub unit. Okay, this hub unit, first of all, it is connected with the gearbox through the main shaft, and the gearbox is connected with the generator. This is also a shaft area. Okay, here we are using the brake. All of you see why we are using the brake system. Suppose the wind speed is very huge, very high. At the time, if it is rotating means it will damage the wind plant, it will damage the wind blades, it will damage the generator also. At the time, we need a brake, mechanical brake alone. At the time we are using the brake system. So normally the safe region for utilizing the wind plant is 12 meters per second. Wind speed is 12 meters per second to 14 meters per second. Suppose the wind, so this is the optimal range of wind power generation, wind range for generating the electrical energy. Suppose if it is less than 12 meters per second means that speed is not sufficient to generate the electrical energy. Suppose if it goes to beyond 14 meters per second means that speed is not suitable, because that's a high speed, is not suitable to generate the electrical energy. It can generate, but the speed is uh, greater than the permissible or allowable limit. So during this permissible and allowable limit violation, it will damage the mechanical breakage of the wind blade, and the electrical breakage of the generator is also possible. At that time, suppose the wind speed is greater than the 14 meters per second, we are safe to stop the generation, stop the rotation of the wind blade and generator. So that can be done by using the brake system. By using the brake system, suppose the wind speed is very high, at the time we can brake and we can stop the rotation of the wind blade and rotation of the generator. Students, can you able to understand what I told here? Students, anyone give the reply? Ganesh Babu, Hemavadi, Hindu Priya. Students, can you able to understand what I told here? No one give the reply. Madhumida, Rupan, Aishwarya, Adi Sharma.
அன்மியூட் பண்ணிட்டு யாராவது ரிப்ளை கொடுங்கப்பா.
Students, can you able to understand? Bonis, is it audible?
அது சார் வெரி கிளியர் சார்.
Okay, thank you. Okay, so the next one, okay, we come to the this portion. Wind turbine blades. To just come to the wind turbine blades. Here, we just take the first one. That's the blade tip speed. Tip speed. Here, this portion you just take. That's that area. That's the end or tip of the blade decides the speed of the wind turbine. This is the pitch control, and it is a two-blade system. Normally, the two-blade systems are suitable for the low power generation. In general, we are using the three-blade system. Common utilization, common generation is 2 megawatts. And nowadays, in European countries, they are moving to the 4 megawatts and 6 megawatts also. So here, 2 megawatts is the basic model. In our India, less than 2 megawatts, that's a 1 megawatts or 500 kilowatts are also available for the wind generation. But nowadays we are moving towards the direction of 2 megawatts or more than 2 megawatts for single power plant, single wind power plants. Okay, so in our India, we are utilizing the 1 megawatts or 2 megawatts in general. In general, we are utilizing that that range of power generations. And the next one, we go to discuss about the wind power fundamentals. What are the fundamental for the wind power? Here, why we are going to this discussion? Actually, what is the basic of the wind power generation? So we are discussing some concept about the horizontal axis and vertical axis wind power plants. But apart from that, normally everything is having certain basic conversion process. For example, hydropower plant means the hydro energy is converted into mechanical energy. Then the mechanical energy is converted into electrical energy. Conversion is there. We cannot directly produce the electricity. There is no possibility to produce anything without any dependent. That's not possible. The God is having only rights to produce everything. We are just doing the conversion process. For example, in thermal power plant, first of all, the hydro is converted into steam. Then the steam energy is converted into the mechanical energy. Then the mechanical energy is converted into the electrical energy. So these are all the conversion process. Here also, we are doing the same process, same conversion process. This is the wind blade, and it is connected with the generator. Okay. First of all, the wind hits the wind blade. Okay, so this is the wind energy. Okay. Now this wind energy hits the blade, so the blade is rotating, so that the wind energy is converted into the mechanical energy. Okay, then it is the shaft of the wind blade and generator both are mechanically coupled, so that the generator is rotating and we can get the electrical energy. So this mechanical energy is converted into the electrical energy. This mechanical energy is converted into the electrical energy. So how many conversions are there? Wind energy is converted into mechanical energy, then the mechanical energy is converted into the electrical energy. There is some three conversion processes there. So what is the resource here? The wind is a resource. This is input. What is the output? Electrical energy is a output. Intermediate energy is the mechanical energy. Intermediate energy is the mechanical energy, so that suppose you just assume the wind power or wind energy is equal to zero, automatically the output electrical energy is equal to zero. So the electrical energy generation in the wind power plant is only depends upon the wind energy. So that we have to calculate the wind power. So the wind power, it depends upon the amount of air, that's a volume of air, then speed of the air, that's a velocity. Suppose the volume of the air is more, but the wind flow is less, means we cannot generate the electricity because it cannot be able to rotate the wind turbine. But okay, velocity is also very important parameter. The mass of air, that's a energy density, that's a air density. So these three important parameters are very mandatory for generating the electrical energy. So here we come to the kinetic energy. Why we are taking the kinetic energy here? I don't mention the kinetic energy up to this discussion. I was already mentioning the wind energy, mechanical energy, electrical energy. Suddenly, I am introducing one more term, kinetic energy, because the wind hits the turbine blade, automatically the wind blade starts to rotate. That energy is called as the mechanical energy. It rotates the turbine, so that is called as the kinetic energy. The mechanical energy is specified as the kinetic energy. Okay, so that kinetic energy is specified as half into m into v square. That's a volume. Okay, mass of the wind, volume of the air. Okay, then we have to convert into the power. From the kinetic energy, we converted into the power. Power is equal to half into m dot. Into that is m dot is called as the mass flux, mass air. That's a dm divided by dt. That is the mass of the air with respect to the time. Why we are taking the with respect to the time dm by dt? That's a differentiation of the mass of the air divided by the time. Why we are taking the differentiation here? Because the differentiation and the integration both are only applicable to the variable quantities. Constant quantities we cannot apply any differentiation or integration. If you apply it, the output is immediately zero. Okay, but the mass of the air is changeable quantity with respect to time. Then only we are taking the dm divided by dt, that's specified as the m dot or m, whatever the cases. Okay, so this is the power equations. This is the power equation. So from this power equations, I further write this equation of into rho a v cube. Okay, that rho is nothing but an air density. Air density, air density, kilogram per meter cube. Okay, a you already known about the a. Okay, and v is the volume. Okay, so a is the v is the cube of the velocity. A is the rotor shift area, that's a pi r square. So how much amount of area which is occupied by the wind on the wind blade, that is called as the shift area. Okay, so this is the wind power fundamentals. So here I just give some definitions of the wind power fundamental. The first important definition, that is called as the cut-in speed. Okay, so this cut-in speed is the minimum wind speed. The word simply everybody can easily understand the statement. The minimum wind speed at which the blades will turn and generate the usable power. So the minimum wind speed for generating the electrical energy, then that speed is called as the cut-in speed. That speed is called as the cut-in speed. Normally that range is 10 to 16 kilometer per hour. The speed of the wind, 10 to 16 kilometer per hour. This is the called as the cut-in speed. Okay. The next one, rated speed. The rated speed is the minimum wind speed. So students, after this presentation, I will share the screen to your head of the department, Dr. Bhumis. So those who are need the screen PPT, you can collect. You can collect from your HOD. Okay. So the rated speed is the minimum wind speed. So it's a minimum wind speed. Both the statements are same, but definition is different. Okay. Minimum wind speed at which the wind turbine will generate the designated rated power. Here, what's the difference between the cut-in speed and the rated speed? Means cut-in speed to generate the minimal power, that's a usable power. But here, rated speed means to generate the rated power. So that is the difference between the cut-in speed and the rated speed. So normally, this 10 kilo, for example, if you take a 10 kilowatts wind turbine means we require the rated power generation minimum 40 kilometers per hour of the wind speed. Suppose if it is less than the 40 kilometers per hour, we cannot generate the rated power. That's a 10 kilowatts cannot be generated. Okay, so the rated speed for most of the machine is 40 to 50 kilometer per hour. Okay, students. And the next important definition is cutout speed. The name indicates we can switch off abnormal speed, that is specified as the cutout speed. Abnormal wind speed. So if the wind speed is abnormal, for example, cyclone condition, the wind speed is very huge. Suppose the wind blade, it may rotate during that speed condition, means what will happen? It break the wind tower. Totally the wind tower will damage. It break. Okay, so that at a very high wind speeds, for example, 72 to 128 kilometers per hour. Normally, it's during the cyclone conditions. It's during the cyclone conditions. So, during the cyclone conditions, the wind speed is very huge. Suppose if you operate that wind turbine during that speed, what will happen? It totally damage the wind tower. The tower is charged. Okay, at the time we cheese the or we break the wind turbine. We break the wind turbine and we shut down the power generations. Okay, so That speed is called as the cutout speed. So it's look like a shutdown to switch off the windmills. So that is called as the shutdown occurs is called as the wind, that's a cut out speed. Okay, so during this huge speed, for the safety precautions, the lot of safety measures are there. We stop the wind turbine rotations. So it avoids, if you break the wind rotations, wind turbine blades, automatically it avoids the unnecessary fault or damage of the windmills. Okay, then the next important, very important definition of the wind turbine is tip speed ratio. Tip speed ratio here is given by the dividing of the speed of the tips of turbine blades by the speed of the wind. So based on the tip speed ratio only, we can get the useful conversion of the electrical energy from the wind energy. That can be calculated. This is the very fundamental law. For example, I think everybody is a electrical engineering students, which is our fundamental law, Ohm's law. So V is equal to IR. V is equal to IR is the Ohm's law. This is the DC supply. AC supply means V is equal to IZ. That's the AC supply. Okay, so this is the fundamental. Whatever the discussions, that will obey the V is equal to IR or V is equal to IZ. Similarly, the tip speed ratio is the very fundamental definition of the wind turbine, wind energy conversion system. So the optimal tip speed ratio depends upon the number of blades in the wind turbine. Okay, you just to take this the hub. So we are using one blade or two blade or three blade or four blade or n number of blades. But which one is the optimum? What is the meaning of optimum? How to get the maximum energy, electrical energy from the wind source. Okay, so throughout the worldwide, the three blades are giving the optimal tip speed ratio, effective energy conversion. That's the wind energy conversion to electrical energy. Then only in home also we are using the three blade fans. Almost some places we are seeing the four blade fans, but four blade fans does not give the good quality of air. Three blade fans gives the very good quality of air, and a huge amount of air can be produced by three blade fan only. Then only normally the ceiling fan is only designed for the three blades. So if you add four blade, five blade, everything is possible. But which one is the optimum? What is the meaning of optimum? So at low wind speed, how to get the maximum electrical energy? So the three blade system is the optimum. Then only we can take the optimum to speed ratio depends on the number of blades in the wind turbine. The fewer the number of blades, the faster the wind turbine rotor needs to extract the maximum power. So this can be done by the three blade. But the three blades are arranged at the equal distance interval. For example, this is the blade 1, 2, 3 is there. So it is arranged at the circular one. So 360 degree divided by how many blades are there? Three blades, you can get 120 degree. So the distance between the first to second blade is 120 degree. Second to third blade is 120 degree. Third to first blade is 120 degree. So that the balanced system can be possible by using this equal distance uh, interval for arranging the blades. Okay. The next one, suppose if the tip speed ratio is very low, it's a speed of the wind is very low. But so it's very simple. If poorly designed rotor blades are used, the wind turbine will tends to rotate very slow, or stall. Stall means almost stop condition. Suppose, for example, I want to, in second point, I want to give one simple example. நம்ம எல்லாருமே சின்ன வயசுல இந்த பேப்பர் காத்தாடி செய்வோம். ஐ திங்க் எவ்ரிபடி ரிமெம்பர் தட். லேசா வச்சாலே இப்போ ஃபேன் கிட்ட வச்சாலே இட் தட் paper blade is rotating very high speed. Is it correct, students? It is rotating very high speed. So, but what is the moment of inertia of the blade? It's very less. It's very less. It cannot able to generate anything because the weight is very thin. Weight is very less. Size is very small. Okay, so that then only that paper blade நம்ம சின்ன வயசுல விளையாண்டது paper blade speed is very high but we cannot utilize that energy. So similarly, if the tip speed ratio is too high, blade is rotating very speed. In which condition the blade is rotating very speed? Suppose the blade weight is very thin, very less. At that time, the blade is rotating very high speed, but the useful conversion is very poor or almost equal to zero. So the turbine will spin very fast through turbulent air. The power will not be generated. That is the point here. The power will not be generated. Blade is rotating, but what is the output? If you connect the generator with the turbine blade, immediately the turbine blade comes to stop. Into. So there is no any usage. So at ideal condition it can rotate. If you connect the generator through the gear box, it cannot generate. So that the blade weight is also acting as a very dominant role for generating the wind energy to the electrical energy. From the wind energy to the electrical energy, so that the tip speed ratio. So from this discussion, the tip speed ratio should be maintained at the optimal value. Optimal value. Suppose it is too low or too high, we cannot generate the proper electrical energy from the wind turbine. So that the optimal tip speed ratio is very important parameter for generating the good quality of electrical energy from the wind energy. Okay, students, shall I go to the next one? Bets limit and power coefficient. These are all some. I am giving only the overview. I am not taking any in-depth discussion here itself. I am taking very basic discussion. Students, anybody give the feedback? Students, anybody give the feedback here? Can you able to understand what I told here? Students, anybody give the feedback? Bharatwaj? Anybody give the feedback, students? Mahalingam? Yes? Rajesh Kannan? I hope everybody concentrating here. Okay. The next one I go to discuss about the Betts limit and the power coefficient. So it's only for find out the efficiency of the wind power. So how to discuss about the efficiency? Whatever the innovations we are calculating the efficiency. What's the in general? What's the formula for efficiency? Efficiency is equal to output power divided by input power. Suppose if the efficiency is high, we can get the very good quality of machine and we can extract the more energy from the machine itself. It's a quite normal one. So this limits, for example, the power coefficient Cp, that's specified as Cp, is the ratio of power extracted by the wind turbine to the total contained in the wind sources. So how much amount of energy is extracted and how much energy is available in the wind. Okay, that is specified as Cp is equal to Pt divided by Pw. So the turbine wind power is equal to half into rho A into V cube Cp. That's the Cp is the power coefficient. Power coefficient. V is the air volume. A is the shift area. We already shift area. This is the air density. air density. So the maximum possible limit of the Betz limit is Cp is equal to 16 divided by 27. So the best energy we can extract at 59, almost equal to the 60 percentage. Almost we can generate the electrical energy from the wind is 60%. In solar means almost 25 maximum. It's a maximum we can get the 20 to 25 only. Okay. So now lot of inventions, research work is going in the solar for the hybrid solar PV systems for getting the more efficiency. But anyway, it's going on. But in future, definitely we will get the more electrical energy from the solar. In wind, we can get the maximum power, maximum efficiency is 60 percentage. And one more factor is capacity factor. This capacity factor is equal to average output divided by the peak output. So it's almost equal to the 30 percentage. Okay. The next important point is the lift and drag forces. What is the meaning of lift and drag forces? Okay, it's a force. The terminology indicates it's a mechanical quantity. No, நம்ம மெக்கானிக்கல் தான் டிஸ்கஸ் பண்ணிட்டு இருக்கோம். We didn't go to the electrical side. The terminal goes to the uh, terminology goes to the mechanical forces. For example, this is the wind blade. You just see the first diagram. Here, the wind flow direction is like that. Okay, the wind flow direction is like that. Okay, you take the first figure one. This is the blade. Okay, this is the wind flow. This is the wind flow. Okay, so if the force which is coincide or parallel with the wind flow, then that force is called as the drag force. That force is called as the drag force. Suppose the force, if you take the force at vertical to the wind direction, that is called as the lift force. That is called as the lift force. Very simple. These two forces deciding the speed of a wind blades. Yeah, just now I told this is the perpendicular to the airflow and it's a parallel to the airflow. The parallel to the airflow is called as the drag force. Perpendicular to the airflow, that is called as the lift force. Okay, this is just now I told here. Yeah, you just come to here important point. Blade element theory. So Betz limit, tip speed ratio. Then next important theory is blade element theory. Actually, it's a lengthy derivation, but I am taking only the outline of the blade element theory. Based on the lift force and drag force, we can form the two formulas based on the blade element theory. Why it's called as the blade element theory means drift and the draft force both are activated along the blade alone. Okay. Anyway, based on the wind which is hitting on the blade, we can segregate these forces into vertical quantity and horizontal quantity. The horizontal quantity, that means that's a parallel the wind force which is the force which is parallel with the wind flow direction, then that is called as the drag force. Suppose it may be that force which is taken as a vertical to the wind flow, that is called as the lift force. Okay, so based on these two discussions purely taken as a blade, then only that theory is called as the blade element theory. Okay, that is Fl is equal to, this is a constant. Okay, constant of the lift force and Cd is the constant of the draft force, drag force. So of rho W square BC, where B and C is the horizontal distance. B stands for the horizontal distance and C stands for the vertical height. Okay, W is the wind hitting velocity. Okay, so that ratio, uh, gear ratio, that's specified as CL divided by CV, that's called as the glide ratio. That's called as the glide ratio. The glide ratio is nothing but CL divided by CD. So we are interested in at high glide ratio for wind turbines as well as for the airplanes. If the glide ratio is very high, good, then automatically we can get the good conversion of electrical energy from the wind energy sources. Okay, okay, these are all general things. Now, up to this, we are discussing about the uh, wind and mechanical technology, where that's horizontal axis, vertical axis. Then we take some important definitions. That's a cut-in speed, cutout speed, critical speed, tip speed ratio, beds limit, blade element theory. Now we are coming to the generator. So up to this, what we discussed, I just okay, this is the turbine. Okay, gearbox is that. This is the gearbox. This is the generator. Okay, so we are discussing about this portions only. Gearbox is the mechanical unit, so that I don't concentrate about the gearbox. Up to this, up to the discussion, last 1 hour discussion, we are taking only the two portions. One is the arrangement of the wind turbine, whether it's horizontal axis or vertical axis, and afterwards we will discuss about the cut-in speed, cutout speed, and tip speed ratio, uh, beds limit, and blade element theory. Blade element theory. So now we are coming to the generator side. Okay. So normally there are three types of generators which are used to generate the electrical energy from the wind energy. One is the self-excited induction generator. Then that is simply called as SCIG. The next one is the doubly fed induction generator, that is specified as the DFIG, and the third one is the permanent magnet synchronous generator, that is specified as the PMSG. Okay, self-excited induction generator. 10 years before we are regularly utilizing the self-excited induction generator, but nowadays we are more concentrating about the doubly fed induction generator and the permanent magnet synchronous generator. Okay, so anyway, yeah, here. Uh, yeah, first of all, we come to the afterwards. We will come to these portions. The power electronic conversion portions. We will come to here. First one, we come to the self-excited induction generator. How to generate the electrical energy from the self-excited induction generator. Topic number one. I need another 15 minutes for completing this portion. Bonus, bonus. Shall I continue up to another 15 minutes?
Yes, sir. Continue பண்ணலாம் sir. No problem.
Okay, thank you, thank you, thank you. So this is the self-excited induction generator. Is there? Otherwise, it's SCIG means squirrel gauge induction generator. Squirrel gauge induction generator or SCIG, both are same. Self-excited induction generator. It is mechanically coupled with the wind turbine. Wind turbine is the this is the gearbox. Okay, it is mechanically coupled with the wind turbine. Okay, so now it generate the electrical energy is that it generate the electrical energy But actually here one more important point is that we are using the converter in this area. We are using the converter in this area. Why we are going to use the converter? I will come this diagram. Yeah, you just take this portion. This is the you just take this is the SCIG. Okay, so here this is the SCIG is there. It's connected with the mechanical, connected with the wind turbine through the gearbox. Okay, but the output of the SCIG is a variable quantity because the wind speed is a variable one with respect to change in time, so that this SCIG generates the variable voltage and variable frequency. Variable voltage and variable voltage and variable voltage and variable frequency. Okay, but this variable voltage and variable frequency cannot directly connect with the grid system because the grid is the constant voltage and constant frequency. For example, if you take a 11 kilovolt, means it's a 50 hertz. Okay, but you already know this the connection of grid with the wind power plant is the parallel operation of the AC system. So this variable voltage and variable frequency must be converted into the constant voltage and constant frequency. So that can be done by using this converter system. It's a pure power electronics converting system. It converts constant voltage and constant frequency. For example, we can get the 440 volt to 50 hertz. Okay. So now, but what is the grid supply? 11 kilovolt. So we are using the step up transformer. So this 440 is converted into 11 kilovolt. So we can get the 11 kilovolt 50 hertz. Then only we can interconnect this SCIG output to the grid. So directly it is not possible. We need a power semiconductor devices, power electronic converter system. Okay. So in this diagram, the converter is placed here only. Actually, it is hidden here. Actually, that's a magnetic component. The converter is there. So what type of converter we are using? We will come. What type of converter we are using here? Because this converter converts variable voltage, variable frequency into constant voltage, constant constant frequency. So it is acting as a very dominant role. When it is constant voltage and constant frequency, then we give to the transformer. Okay, so now it is stepped up. Now it is stepped up by using the step up transformer, and it is given to the distribution stage. Okay, then at the grid side, the transformer is there. Depends upon the grid voltage, whether it may be 32 kilovolt or 110 kilovolt or 132 kilovolt or 230 kilovolt or 440 kilovolt or 660 kilovolt, whatever the cases. We have to step up or step down. Okay, suppose that this output is 11 kilovolt. For example, their distribution side 11 kilovolt 50 hertz means the grid voltage is 32 kilovolt 50 hertz. So we need a step up transformer. So this transformer is 11 kilovolt to 32 kilovolt. Now automatically we can get the 32 kilovolt 50 hertz, then it is interconnected. Okay, so we can, by using these coral gauge induction generator, we can generate the electrical energy. Okay, here everything is okay, but which one is acting as a very important role here? Converter. Without converter, we cannot convert into the variable voltage, variable frequency into the constant voltage and constant frequency. That's not possible. So the converter is a very important component, important power electronic component in the wind energy conversion system. So now we come to the converter side. What are the various types of converter topologies here? Okay, the converter is used to convert variable voltage, variable frequency to constant voltage and constant frequency. What are the different types of topologies here? First one, in general, several types of converters are there. I just take some topologies only. Okay, for example, the first one, I take this is the first one, the diode and pulse width modulator voltage source inverter converter unit. Okay, so here you just take this is the squirrel gauge generator SCIG. Okay, the output of the generator is given to the diode. What is the first step? This total unit is the converter. Okay, this total unit is the converter. So the first step, what is our ultimate motto? Here we can get the variable voltage and variable frequency. I need the constant voltage and constant frequency at the output side. At the output side. Okay, so that the first one, this is the AC supply. The output is also a AC supply, but I first step I convert this variable voltage, variable frequency AC supply is converted into the DC. So this AC is converted into DC. So this unit is acting as a rectifier. This unit is acting as a rectifier. Why? First conversion, so from direct variable voltage, variable frequency to direct AC constant voltage, constant frequency is very, very toughest task. Okay, then only we can convert the AC into DC, then DC into AC. Okay, then here we are using the coupling capacitor. So this coupling capacitor is used to reduce the ripple factor. That is, it's act as a filter circuit. It acts as a filter circuit. So the output of the rectifier is DC, but this DC is having some AC content. Okay, so that this unwanted AC element which are available in the DC is filtered, so we can get the pure DC here itself. Pure DC here itself. Now, this DC supply is converted into AC supply by using the inverter unit. So, the inverter unit converts the DC into AC. So, we can get the constant voltage and constant frequency. Now, this constant voltage, constant frequency is connected with the grid. This is the first one. The next one, we come to the diode to DC chopper and pulse width modulator. So here we are using the in inverter side transistor and a diode or IGBT, whatever the cases. Okay, depend a lot of power semiconductor switches are there. You already know basic is diode, thyristor, transistor, IGBT, triac, diac, MOSFET, JFET, a lot of power semiconductor devices are there, but it's only a switching device. It's only a switching device, but huge. That's the frequency range of switching is it may be in kilohertz or megahertz. Okay, so it's a switching device. So the next model, this is the second one. The converter is here we are using concept is same. It's used to convert the AC into DC. This is the chopper circuit. This is acting as a filter unit, and here we can get the DC into AC. Then it's gridded. Okay, so depends upon the requirement which one is the suitable for the particular application we can choose. Okay, the next one, the third one. Here we come to the third one. Back-to-back pulse width modulator voltage source inverter. So here we are using the voltage source inverter. This is rectifier. This is inverter. Both are similar design. Okay. So, but anyway, this unit is for the filtering purpose. Okay. So the next one, this converts into AC into DC filter, then DC into AC, constant voltage, constant frequency. Here variable voltage, variable frequency, and it is connected with the grid. Okay. The fourth one, you come to the fourth basic topologies, diode and line commutation with converter combined with the reactive power compensation. Okay. So here we are using the rectifier, inverter, then we are using the reactive power compensation units, and the last one is the matrix converter. The fifth one is the matrix converter. Fifth one is the matrix converter. In this matrix converter, uh, n number of semiconductor switches are connected in series parallel. Okay, series parallel. So by this way, effective conversion is possible. So by this effective conversion, the grid interfacing is most effective than the other converter topologies. Okay, so here, which type of converter is preferable, you can choose. Okay, the next one, channel controller, that's not needed. Uh, okay, this I think these are all the basic one. The next converter is the doubly fed wind energy systems. So doubly fed induction generator means here we are taking the power from the two portions. One is taken from the stator and another one is taken from the rotor. Another one is taken from the rotor. In stator, we take the power directly from the stator itself. But rotor, you just take which type of rotor is used here? We are using the slip ring type of rotor. Slip ring rotor. So we can get the slip power here itself. Slip power here itself. So this slip power is almost 30 percentage of the rated power only. Only for example, 300 volt is output for our AC convenience. We are taking the 300 volt means so 90 volt supply is available from the rotor itself. It's only an example, but actually we are not using the 300 volt. It's not a standard voltage source. Okay, so now here this power in stator power, it's directly connected with the transformer. This is the power which is taken from the stator. That's the first fed power from the doubly fed induction generator. Second one, that slip power which is taken from the rotor is connected given to the rotor, so that this low voltage, low frequency, same thing. It's a variable voltage and variable frequency, so that this low voltage, low frequency, and variable voltage and variable frequency is converted into DC. So now it is converted into DC, and this is the filtering unit. It is used. It's a DC ripple. It can eliminate the unwanted content in the DC output. So this is the filter. Okay, the hour and this DC is given to the stator side converter. Why it's called as the stator side converter means it is connected with the stator of the doubly fed induction generator. Okay, so here it can convert into the constant voltage, constant frequency with the rated value. Rated. And it is fed to the stator side. It is fed to the stator side. So the two powers are fed to the grid side, then only it is called as the doubly fed induction generator. Okay, so it is given to the transformer as usual. The remaining concept is same. Step up transformer is there. This is the distribution side. Depends upon the grid voltage, we can further step up or step down. That can be done here itself. And the power which is generated from the doubly fed induction generator is fed to the grid. So this is the stage 1 power, which is taken from the stator, and the second power is taken from the rotor, so that double power is fed to the grid. Then only it's called as the doubly fed induction generator. So here also we are using the converters. In these converters, we already saw the 5 different topologies of the converter. We can choose which one is the preferable to the particular power generating system, we can use that power electronic converter here itself. Okay, this is the equivalent circuit. I think that's not needed here. Then the next one, wind power system operation. So we discussed about the two generators. One is the SEIG, self-excited induction generator, or SCIG, squirrel gauge induction generator. Then doubly for the induction generator. Both are induction machine, induction generator. Okay. Now we compare the SCIG and DFIG. Which one is better? So SCIG we can take only one power. DFIG we can take the two power. One is taken from the stator and another one is taken from the rotor. So automatically we can get the more power from the DFIG. Okay. So that you just take DFIG power is greater than the SCIG power. That is the conclusion based on the comparison between the SCIG and the DFIG. Okay, students. Okay, students, can you understand? And one more generator is there. That is the permanent magnet synchronous generator. So SCIG and DFIG both are induction generator. PMSG is the synchronous machine, synchronous generator. Synchronous generator is there. Okay. So nowadays we are moving towards the PMSG. It's having a lot of advantages. Actually, if you take the design aspect of the PMSG, it takes more time also. Okay, so in PMSG, the concept is same. Everything, the concept is same. This is the wind turbine. Here we are using the permanent magnet synchronous generator. Why is it called as the permanent magnet synchronous generator? I just give the outline of the PMSG structure, design structure. This is stator. We are having the three windings R, Y, B is there, but the rotor is made by the permanent magnet. The rotor is made by the permanent magnet. So then only it is called as the permanent magnet synchronous generator. Permanent magnet synchronous generator. Very simple. When you rotate the rotor, so the flux cuts the stator winding. So as per the Faraday's law, whenever the magnetic flux is cut by a conductor and EMF is induced, we can get the output on the PMSG side. PMSG side. Okay. So that concept is that is the PMSG design. So now it is PMSG rotor is mechanically coupled with the wind turbine. So when the wind turbine is rotating, automatically the rotor is also rotating because both are mechanically coupled. So the permanent magnet flux cuts the stator winding. That so as per the Faraday's law, the EMF is induced. Okay, we can get the variable voltage, variable frequency, or if you use the sophisticated gear, constant voltage, constant frequency, but it's in low range, low value, so that I want to convert into the higher value. So the same concept is repeated here. This is the rectifier unit. So the output of the PMSG is converted into DC, and by using the filter circuit, the DC is converted into AC. This AC is DC is converted into the AC. That can be done by using the inverter. Then it is stepped up by using the step up transformer. So constant voltage, constant frequency with equal to grid parameter, grid voltage and grid voltage and frequency. Then afterwards it can interconnected with the grid side. Okay, so this is the direct driven PMSG. I hope here before we go to discuss about the remaining one, what are the portions we discuss? I just give the summary about the discussion. The first one we discuss about the wind turbine design. That is horizontal axis, and vertical axis. Okay. The second we discuss about some fundamental parameters, fundamentals, that is cut-in speed, cutout speed, tip speed ratio, that is very important one. Tip speed ratio, then its constant or bits limit. Then another one is the blade element theory. Okay, these fundamentals we discussed. Finally, the third portion is the first stage discussion. Second and the third is wind generator classification, SCIG, DFIG, PMSG. Here we are discussing about some topologies and basic structure. I hope the students can understand this overview because I am not taking any depth discussion about the wind turbine design or for Butts law or Brave element theory. Actually, if you take means it takes more time also. I am taking only the fundamental concept and SCIG, DFIG, and PMSG. The lot of research work is also going in this category. But anyway, I am just taking only the fundamental concept about this discussion. I hope all the students can understand this discussion. Students, if you have any doubt, don't hesitate. You just unmute your mic and ask the question to me. I am ready to give the answer to you. Students, please. Students,
Students can raise a question now. If you are having any doubt, you can ask.
anybody having any doubt, students? Don't hesitate.
Third year students,